All right, hello. This is LeetCode 226 invert binary tree. So, given a root of a binary tree, invert the tree and return its root. So, what do they actually mean by inverting the tree? Well, it's like the example one. Basically, given this as being the input right here on the left, this tree, this would be the output. And as you can kind of see, 4 didn't move at all, right? Because it's just in line. But its children flip positions left and right, right? They went like this. They flip positions, and then these guys flip positions as well. So it's almost as if at each layer or level, say this is L1, this is L2, and this is L3. At each level, the nodes are swapped. So in this level, the node would be swapped, and then at this level, the nodes would be swapped, and then at this level, the nodes would be swapped, and so forth. So this behavior just keeps going on until we run out of nodes, until we run out of children to do this too. So you could do this, I believe you can do this using like a breadth first search. You can just kind of go through and maybe swap the children, but I believe you can actually do this recursively. So what you could do is, because you're doing a swapping operation, you'd have to basically grab one of the nodes and store it in some variable, like a temporary variable. Temporary variable, right? And then you could swap this to the left side, and then now you've lost this axis, right? But then you can just store temporary to the right side, and then you continuously just do that action till you run out of nodes to do it to. So you can solve this using recursion. Yeah, so this is actually more simple than it looks, but what we're gonna do is we're just gonna grab a temporary node is equal to let's just say it's root dot left, and then we're gonna say root dot left is equal to root dot right. So this is overriding the left node with our right node, right? With our right child. So in this instance, sorry about that. In this instance, we would be overriding it with this, right? And then we can just override root.right with our temporary node. So we basically done the swap. And then all we have to do is just call self.invert tree with root.left. So we're calling our function. We're using recursion with this left subtree, and it's going to do all these swappings of its subchildren and so forth until it runs out. And then we're going to just do this invert self.invert tree root.right, and then once this all bubbles back up, we're just going to return the root node again. Yeah, I think that's it, unless I'm missing something. Might be missing a test case. Attribute error if none type object has no attribute left. So right. I think this is an instance of. I think I didn't look at something right in the constraints, right? We could possibly have 0 nodes, so there's an instance where root can be none or null, if you're familiar with that. So if root is equal to none, then return none. Basically, none is Python's version of null. Right. I think this will pass that test case. Yeah. Okay, so yeah, this is invert binary tree. So let's go ahead and try to find the time and space complexity. So let's see. Time complexity. Let's go ahead and start with the space. I think the space is a little easier to understand. I think the space would be O of 1 because we are using some extra variables, right? Right here, just temporary node. But this variable is not going to scale as our input grows. However, now that I just thought of it, I think I haven't used recursion in a while, and I think that we might be using a stack by using recursion, right? The call stack. So I think it's either O of 1, or if we're taking into consideration the call stack, then it might actually be O of n, because the stack might grow up to size n, where n is the size of the number of nodes in the tree. And I think the time is O of n, where n is the amount of nodes in this tree. I'm not too sure about this because it's been a while since I did the time and space complexity, but give me 1 second and I'll try to confirm this by searching online. Okay, so I found this article, and basically they fleshed out the recursive version of this invert binary tree, kind of to what we did over here. And I think what they're saying is that the time complexity is O of n, so it is what we have here, where n is the size of the number of nodes in the binary tree, but the space would be actually O of the space would be not this, but it would be O of h, where h is the height of the binary tree. So the height would be 1, 2, 3, I believe, in this case, because there's like 3 levels, because that's for the call stack. Yeah, so that explains the time and space complexity. So yeah, thank you for watching.